Let's explore a fundamental question about the complex systems we rely on every day. Why do they so often seem to push risk outwards, to the very edges of their structure, right up until the moment they fail?
When a large system fails, our first instinct is to hunt for the mistake. We look for that one broken part, the single human error, that one-off accident. But what if that entire assumption is flawed? What if failure is rarely an accident? What if it's actually the predictable, even logical result of the system operating exactly as it was designed?
And that, right there, is the central puzzle we're going to piece together. If every single component is doing its job, if all the rules are being followed, and every target is met, how can the whole thing come crashing down? Well, to understand that, we first need to look at the basic anatomy of a system.
It turns out you can simplify almost any complex system into just two essential parts. There's a core and there's an edge. And this simple model is really the key to seeing how pressure can build up, completely unseen.
The core is the part of the system that's built for performance. It's focused on optimizing all the things we can see and measure, like speed or output or efficiency. It gets all the attention. The edge, on the other hand, is different. It's often a shared, less visible part of the system, and its job is to quietly absorb the hidden consequences of what the core is doing. So, to make this idea really concrete, let's build a very simple system here. We'll use a network of processing nodes, and we're going to watch how this little system behaves as we go.
In our network, the individual processors, those are the core. Their one and only goal is to complete tasks as quickly as they possibly can. But all that work creates a byproduct, heat. And that heat is handled by the edge, which in this case is a single, shared cooling system that serves all of the nodes at once.
So what is the mechanism that actually drives risk from that high-performing core to the quiet edge? Well, it's rooted in a really basic economic concept, the difference between the costs that a decision-maker pays and the costs that everyone else is forced to pay for them.
A private cost is pretty straightforward. It's what you pay directly when you make a decision. It's the cost that's visible, it's immediate, it's the price on the sticker.
An external cost, though, is the hidden part of the transaction. It's the cost that gets pushed onto somebody else, an unpaid bill, that the larger system sooner or later is going to have to settle. So you see, the true cost of any action is actually these two parts combined. The part you see, the private cost, and the part you don't, the external cost. And this is precisely where the trouble begins.
And this is the crucial insight. The core of a system is almost always designed to focus only on its private costs. Why? Because that's what directly impacts its visible performance metrics. Those external costs are, by design, someone else's problem.
Let's go back to our network. Say one processor overclocks itself to boost its speed. The private cost for that processor is tiny, maybe a little extra power consumption. But the external cost, a significant amount of extra heat that gets dumped right into that shared cooling system. The processor scores a local win, but it does so by making the shared edge work harder.
Now, on its own, one processor offloading a little bit of heat isn't a big deal. The real danger emerges when countless small, perfectly rational decisions like this start to add up over time, creating a deep and hidden vulnerability.
So imagine every single processor acting logically in its own self-interest adds just a little more heat to the system. Each individual decision makes perfect sense, but taken together they're creating a silent, accumulating crisis for the shared edge.
And this is what creates such a dangerous illusion. The system's visible metrics, which are driven by the core, look better than ever. Processing speeds are at an all-time high. But underneath all that success, the edge, which is absorbing all these hidden costs, is being silently pushed closer and closer to its breaking point.
Our cooling system is still working, of course. There are no alarms going off. But with every single bit of extra heat it absorbs, its capacity to handle a sudden shock, which you might call its safety margin, is silently shrinking. A fragility is building, and it's completely invisible to the high-performing core.
And then eventually the inevitable happens. A tiny disturbance at the now fragile edge is all it takes to trigger a catastrophic failure that cascades right back into the very core that created the problem.
The collapse happens like a chain reaction. First, a small, perfectly normal trigger puts just enough stress on the already saturated edge. Then, the edge fails, and suddenly all those costs it was absorbing flood right back to the core. But the core was built for pure efficiency. It has no buffer, no defense. And so, it collapses.
Back in our network, a temporary spike in demand creates a slight increase in heat. It's the final straw. The overloaded cooling system shuts down. Instantly, all that heat is trapped at the core. Every single processor, now without any cooling, overheats and fails. The entire network simply goes dark.
And this brings us right back to where we started, to that initial paradox. The system didn't fail because something went wrong. It failed because everything went exactly right, at least according to its own internal rules.
That final collapse wasn't some random, unpredictable event. No, it was the direct and predictable consequence of a fragility that had been systematically constructed, one logical decision at a time.
When you look at it this way, every part of the system did its job perfectly. The processors maximized their performance, the cooling system absorbed the heat right until it couldn't. The failure wasn't a bug in the system, it was a feature of a system designed to ignore its own side effects.
And this reveals a fundamental paradox that sits at the heart of so many complex systems. The very same drive for efficiency that makes a system appear strong is also what creates the brittleness that can, eventually, cause its downfall.
Which leaves us with one final question to consider. If optimizing a system for peak performance can also make it incredibly fragile, what then is the true, total cost of that optimization?